All right, so in this video, we are going to be talking more about section 3.1, and we'll be solving exponential functions in context. So my goal is for you all to be able to use rate of change to solve exponential problems, and also to be able to solve problems involving compound interest. So first of all, recall that our exponential function, the general form for it is given by f of x equals a times b to the power of x. Now in this case, a is the initial value, or the y-intercept. We already talked about that, but we haven't really talked about what b is yet. Now, the reason we use b is because that stands for the base of the exponent, but really what's going on here, specifically when we're solving functions in context, is we're going to end up with b equaling 1 plus r, or b will equal 1 minus r. And in this case, r represents the growth or decay rate of whatever we're looking at. So in this case, if I had a 1 plus r, that would be growth. And if I had a 1 minus r over here, that would be decay. So here's what we mean. Let's take a look at an example right off the bat to try to wrap our heads around this. So if you look this up online, you can find the population of the United States pretty easily. And when I did this, the population for the United States in 2018 is what it gave me, was about 327.2 million. And the growth rate, this is a little bit harder to find, but the average growth rate for about the past decade was about 0.66% per year. And we're going to assume that this population is growing exponentially. Most populations do follow an exponential model. Not perfectly, because things are a little bit unpredictable in real life, but it's a pretty close model. You can pretty closely model the population using an exponential equation. So what we're going to do is a couple things. The first thing I want to do is create a table for the population from 2018 until this year, which would be 2020, assuming that the growth rate remains constant. So here's what we're going to do. Let's set it up so we have time in kind of the x position, and we'll say p for population in the y position. So at time 0, instead of using 2018, oftentimes we say 0 to say that's where we're starting. The initial population was 327.2, and this is in millions. This way, I'm actually starting on the y-axis because this will be my initial value, or my y-intercept. You can always do it at 2018, but usually the models work better if you start at 0. Okay, now after 1 year, so 2019, I need to figure out what this is going to be. So to figure that out, I'm going to take 327.2. I'm going to figure out what 0.66% is, and in order to do that, you have to convert the percent to this decimal. So keep in mind 0.66% means 0.66 per 100. So you're dividing by 100, and you end up with 0.0066. Okay, so back to the problem. We're trying to figure this amount out. So we take 327.2, and we're going to multiply that. I'm going to do that on my calculator. So when I do that, I get about 2.15, I'll call it about 2.2 million. So then my new population is going to be 327.2 times, or sorry, plus 2.2, and so I end up with 329.4. And that's what's going to fill in the place of this question mark over here. So I'll erase the question mark and replace it with 329.4. Now, this is fine. You can multiply and then add, but a shortcut to that is to do it all in one go and multiply by 1 plus 0.066. And this is hopefully going to look familiar to what I'd mentioned up here with the growth rate. The base of our exponent is going to be 1 plus r. And here's why. Because when you multiply this, you should end up with about the same, well, you should end up with the exact same thing. Let me make sure I'm not doing anything wrong by plugging it into the calculator. I get 329.36, so I'll say that's 329.4. And so that does agree. And so then in the next one, we're going to take 329.4 now, and we're going to multiply that by 1.0066. So I'm just multiplying it by 1 plus r here. And so when I do that, I get 331.5 roughly. You might get a different number if you use the rounded version, so let me just double check that. 331.6 is what we'll go with. Okay, so each time I'm multiplying by 1.0066, and that would be the growth in this case. So therefore, the function is population as a function of time is given by 327.2, my initial value, times my base, which is 1 plus r to the power of t. So that would really be part B. I kind of skipped ahead. Part B would say find an equation to model this. And so I already did that up here, but there is your equation. Finally, you'll oftentimes see something along the lines of, what is the population, assuming that this growth rate holds, let's say in 2028. So this would be t equals 10. And now it's just a matter of plugging into your function. P of 10 equals 327.2 times 1.0066 to the power of 10. If we plug that into the calculator, we should get about 349.4 million. Okay. So that's how you would apply this idea of rate of change. Now let's just say, just to kind of reinforce this concept, let's just say that you're given some function, I'll call it f of x. Let's say it equals 231 times 0.89 to the power of t, or sorry, x I'm using now in this case. And I just said, what is, no, first I would say, sorry about the confusion. First I would say something like, is this growth or decay, to which you would respond, well, Mr. Edwards, this is decay. And I would say, well, why is it decay? And you would say, well, that's decay because 0.89, which is B, is less than 1. Whoops. Is less than 1. So B is less than 1. And that's the definition for decay. And then I would say, well, since it's decay, what is the decay rate? And you would say, well, Mr. Edwards, to find that, we would say that B equals 1 minus R, and B is 0.89. So solving for R in this case, you would end up with 0.11. And so you would tell me that the decay rate is 0.11, or you might say 11% as a percentage. Either way is fine. And that would be it. Sometimes you'll see a negative on these, but I'm okay if we're already assuming it's decay, you can give it to me as a positive amount. All right, so there you have how exponentials relate to the real world in terms of context if we have a growth rate or a decay rate. More quantities than you would imagine actually follow exponential growth and decay. That's why we do place so much stock on this. Okay, now the next concept I want to cover was most likely covered in Algebra 2, and that has to do with compound interest. And so what I'm going to do, I'm not going to actually develop the formula. If you're interested in where this comes from, by all means ask. I'm just going to give you the formula in order to remind you. So here is the setup. You deposit some amount of money, which we'll call capital P, stands for principal, into an account, earning an interest rate of R and you leave it in there for T years. The interest, not just interest. The interest is compounded n times per year. The amount, which we'll call A of T, you have after T years is given by this formula. A of T equals principal, so your initial amount, just like we had before. Now your rate is not just 1 plus R, it's actually R divided by N, and the amount of time that passes is not just T, it's actually going to be N times T in the exponent. So once again, we have our principal, our rate, and we have our T years, and then we have N times per year, and then they all show up in the formula. So if we were to do a problem, it would look something like this. You put $1,000 into an account earning, let's say, 4.3% interest, compounded, I'll say the word quarterly. How much money is in the account after, let's just do something like 5 years. Okay, so our principal is 1,000. Our interest rate is 4.3%. Whoa, what just happened? There we go. Our interest rate is 4.3%, which means it's going to be 0.043 if we divide it by 100. N is reflected by this quarterly. That means 4 times per year. And then our time is going to be 5. So I'd say A of 5 equals 1,000 times 1 plus 0.043 all over 4 to the power of 4 times 5. So that means I would end up with, let's do that on the calculator, sorry, the calculator is, let's see, 1,000 times, I'm doing this on my calculator on my computer. Okay, and so I end up with 1,238 and 44. So that means you would have $1,238.44. Quick note on this, when you're doing these problems, if it's compounded yearly, that means that n is just 1. If it's quarterly, we already did that. If it's monthly, that means n equals 12. If it's daily, n would be 365. Semi-annually means twice a year, so that means that n equals 2. And that should conclude 3.1. You should now be able to work on all of the delta math.